solve the equation, right? So let me write down the equation one more time here on from the previous slide. We have I C0 dot, right, equals to B1 E divided by 2m cosine omega 1t, and then e to the power I omega lt C1. Okay, that's how it works. So with this, the first thing I will do is to convert the cosine to the exponential function for some reason. You will see that later. So this is equals to B1 E divided by 4m. I have an extra 2 because I'm going to make this as e to the power I omega 1t plus e to the power negative I omega 1t as the cosine t, right? Cosine theta equals to e to the power I theta plus e to the power negative I theta divided by 2. That's what I'm doing. Cosine omega 1t equals to e to the power I omega 1t plus e to the power negative I omega 1t divided by 2. That's what I have here. The whole thing times e to the power I omega lt. System is not good. I omega lt C1. Okay. Now then I can further combine the terms. I put the terms together. This becomes e to the power I omega 1 plus omega lt plus e to the power negative I omega 1 minus omega lt C1. Okay. Now, if I put omega 1 equal to omega L, what does it mean? It means the magnetic field in the x direction oscillates at the same frequency as the Larmor precession, right? So let me go back to this figure. This magnetic field is oscillating, and at the same time, the qubit is precessing due to this external vertical magnetic field. You can see that once it precesses for one cycle, your magnetic field will go back to the original position. It's just like resonance, right? You feel the same magnetic field when you are at that position, at the same position, right? So with this, second term will be gone, right? Because this will be 0. Then this is equals to 1, correct? Not gone. Maybe let me just write it again. Then I have I C0 dot equals to B E divided by 4m e to the power I2 omega lt plus 1 C1, right? Because omega 1 equal to omega L. Now, this is oscillating at high frequency. Okay, so it changed very fast. On average, it does not have a big effect. So we can ignore it. Okay, and this is the so-called rotating frame approximation that we will discuss more a little bit. Okay, so it's rotating, it's changing so fast, right? Think about this is just a phase, it changed a lot. So in our system, we might not be able to feel it because it's changing so fast. I just feel out FH F on FH, I don't feel anything, right? So as a result, I can write this as Ci C0 dot equals to B1E 4M C1, right? And similarly, I do not show here. You just work on another equation. This is equation 1 from equation 2, right? From the previous slide. Maybe I should just say this is 1 from the previous slide, right? This is this equation. Now we're running this equation. You will get I C1 dot equals to B1E over 4M C0. Okay, so basically we further simplify these two equations to something easier. Okay, then what is the solution? Well, I can now just substitute the equation into it, right? For example, what is C0? I just substitute, I can do a dot. I say the first equation, IC dot dot. I do one more differentiation. I get B1E over 4M C1 dot. But C1 dot equals to the second equation, right? So this is B1E over 4M. C1 dot is B1E over 4M C0 divided by I, right? So C dot dot, I mean this is C0 dot dot equals to negative B1E divided by 4M square C0. Right? So I got a differential equation. But this differential equation is easy. Uh, 12. It's 12 again. Let's look at the equation to solve one more time, right? What is the equation we want to solve? The equation to solve is from last slide. The equation to solve is C0 dot dot plus, I just move it to the left, okay? B1E divided by 4M square C0 equal to 0, right? So if you not familiar, this is again, dot dot means dC0 dt square, right? Second derivative. With, and then plus B1E divided by 4M square C0 equal to 0, right? This is just a second order differential equation, okay? And just check up your differential equation knowledge or Google, you will find that the general equation is C0. This is the solution, second order, right? The solution turned out to be C0 equals to A cosine omega R, I call it dash T, plus I B sine omega R dash T, where I set omega R dash equals to B1 E divided by 4M. Okay, I think that is what I set. Double check. Yeah, that is right. So why do I do this? Because this equation can also just be written as C0 dot dot plus omega R dash square C0 equal to 0. Okay, so this is like the, this is just this one. Okay, this is the general equation, right? So from here, I can also find out what is C1, right? Because what is C1? C1 equal to I C0 dot divided by omega R dash. Okay, so it is I divided by omega R dash and then C0 dot. But I already gave you C0 dot. So, and when I do this dot, I'm going to take out omega R dash because I have a cosine and sine, so they are going to get cancelled, right? So this is going to be equal to negative A sine omega R dash t plus I B cosine omega R dash t. Just because, right, I will take out omega R dash and get it cancelled, right? So this is equals to C1. It is equal to negative IA sine omega R dash t minus B cosine omega R dash t. So this is A. Let me see if that's correct. Minus A cosine. Yeah. Okay. But we have a boundary condition. What's boundary condition? That at t equal to 0, we know that C0, right, must be equals to cosine theta divided by 2 e to the power negative I phi divided by 2, right? Make sense? When t equal to 0. Because that is the initial state of my qubit. And based on the equation here, right? At t equals 0, this term is 0. This is equal to A. So here I get A needs to be equal to this guy. Okay? Then how about B? What I can do is again look at C1, right? C1 at t equal to 0, again, needs to be equal to sine theta divided by 2 e to the power I phi divided by 2, right? If you forgot why, I go to the beginning. This is because of, which one? Here, right? Because of this one, right? We talked about this earlier, right? At the beginning, for any qubit state, it has this, right? So this is the C0, right? Why this is C0? Because when we do the general equation, we assume that our solution is equal to C0 times 0 plus C1 times 1. And when t equals 0, this is ignored, right? So this must be equal to cosine theta divided by 2 e to the power negative I phi divided by 2, right? So similarly for the C1. But at this moment, we use plug into here. This is C1, right? So it means negative B equals to this guy. Okay? So this gives me A and B, right? Therefore, C0 equals to pretty complicated. Cosine theta divided by 2 e to the power negative I phi divided by 2, right? I plug in A, cosine omega R dash divide times T, yeah, plus I, and then we have the B, which is negative sine theta divided by 2 e to the power I phi divided by 2 sine omega R dash T. Okay, now I'm going to do some treatment. What I'm going to do is to take out e to the power negative I phi divided by 2. Now, if I do this, what will happen? Cosine theta divided by 2, and maybe I put it at the front. I take out e to the power negative I phi divided by 2 cosine theta divided by 2 cosine omega r dash t, okay, and then minus I sine theta divided by 2 sine omega r dash t, and then times e to the power I phi, right? Why is that? Because this one times e to the power I phi equal to e to the power I phi over 2. I just take out a common factor, e to the power negative I phi divided by 2. And then I will have the cosine theta, cosine omega r dash t minus I sine theta, sine omega r dash t. Okay, but I want to do one more treatment. Negative I is what? It's just equal to e to the power negative I pi over 2. That is negative I, right? So with this, I can further write this as e to the power negative I phi divided by 2 cosine theta divided by 2 cosine omega r dash t, and then plus sine phi divided by 2 sine omega r dash t e to the power I phi minus pi over 2. Is it minus pi over 2? Sorry, I actually don't want to take the negative I make the mistake. I actually only want to take the I instead of negative I, okay? So this should be negative, and I want to only keep this, make this one. I want to make this one to be e to the power I pi divided by 2, right? So this is plus. This is plus, right? So what I'm trying to do is I want to remove this I. I still keep negative, right? So by I is e to the power I pi. So combined together, this becomes e to the power phi pi over 2. Okay, so I don't have enough slide. I need to add. So I added one slide, right? So why do I want to do this? Let me just finish the C1. For C1, I want you to do it yourself, right? Let's do it in the maybe homework. You will find that C1 is just equals to sine theta divided by 2 cosine omega r dash t plus cosine theta divided by 2 sine omega r dash t times e to the power negative I phi plus pi over 2. The whole thing times e to the power I phi over 2. Now, if I set phi equal to pi over 2, okay, what does it mean? When I say phi equal to pi over 2, I have a, this is y, this is x, right? And this is z in the broad sphere. And also in the real 3D space. And my function is cosine omega 1t b1 in this direction, right? When t equal to 0, I have a magnetic field b1 pointing in the positive direction. If I set phi equal to pi over 2, it means my initial states are those states on the zy plane. For example, they might be, it will be something along this plane, this plane, right, along here. If you do this, I say the wrong thing again, it should be negative pi over 2. Okay, set it to be the negative pi over 2 instead of pi over 2. So in this case, it's not here, but here. Right, on the still zy plane, but you have a state psi here, right? Anywhere along this CY plane. If you do this, e to the power negative I phi plus pi over 2 is going to be equal to 1 because this is 0. Then what happened? Then you will see that this is just sine, cosine plus cosine, sine. And this is cosine, cosine minus sine, sine. Then you find that C0 is just equal to cosine theta divided by 2 plus omega r dash t. And C1 is just equals to sine theta divided by 2 plus omega r dash t. And the whole function is equals to cosine theta divided by 2 plus omega r dash t times e to the power negative I phi divided by 2, 0, plus, not 0, not just 0, right? We still have the Lamarck precession because when we do this expansion, we still have this one, right? And you just plug in, you will get, I just combine them together. It is phi plus omega LT 0 plus sine theta divided by 2 plus omega r dash t e to the power I divided by 2 phi plus omega LT 1. Right? So what does it mean? Besides that, it is precessing about the C axis like before at the Lamarck frequency, right? It's precessing. It also has the theta increasing, okay? And here I will further write it as theta plus omega r t divided by 2, theta plus omega r t divided by 2. So it is with omega r equals to omega, with omega r equals to 2 omega r dash, which is E B D B1, right? What is omega r? Look at this one again. EB1 divided by 4m, here is divided by 2m, is also rotating down by this angular frequency. And this is the so-called rapid frequency. Right? So how does it work? Your state is here, then you will precess, but at the same time, you will keep rotating down and eventually go to the south. And with this, you successfully rotate a qubit from the northern hemisphere to the southern hemisphere. And this is called rapid oscillation. If you keep rotating, eventually you will go back because this theta can become larger than 180 degrees, right? The total theta, right? Now then why do I need to set this? This is not necessary. It's just because I want to fit into this equation. Because the theta is only meaningful when it is straightforward when you have this when your state is on the YZ plane. So when it's going down, the change of the theta is just purely the theta, original theta plus some value. If it is on other part of the broad sphere, it still works, you will still go down. But the theta definitely is not the theta because now the theta actually go, you remember the theta is actually measured from the x-axis to your state. So if you, when you're going down, you are not rotating about this plane. So it's just not a simple theta plus something, but your theta is increasing. Okay, it's just not a simple addition. But if it is on this YZ plane, we can fit into the equation very nicely. Okay, so this is the overview of this rapid oscillation. Okay, I will stop here, and next time I will give some more intuitive way to understand the rapid oscillation. Okay, actually I already done this page. I should let me see. Yeah, maybe next time I will go over this, and then we go to another formalism.